Hello, this is homework 5. Um, like so far, I have graded up to part E, and I find you guys did well this time, and did much better than I expected, and than before. So I'm happy, glad you tried hard. Thank you for your input. And as you see, like as you see, this question one is the simplest possible example we can think of, right? So just one regressor, and it can be endogenous or exogenous. One regressor, one IV, everything is standard. So one more can I do? So I understand it is still difficult, but you have to do the practice once at least once at some point. So I think it's a good chance. Maybe the last time you are going to derive the basic mechanism of the test statistics. So I just wanted you to try this. Otherwise, you will never understand what is going on. So okay, let's see. First, part A and part B is more like a preliminary result. Like there are, by the way, there are many different ways to implement the same thing and to prove the same result. And there may be an easier way to handle this simple example, but I just wanted to guide you toward more general setup, and I'm showing you just one possible way, and by using this idea. So let's see. It's the first two questions are pretty straightforward, and nothing much to say about this. It is just the central limit theorem. But remember, under the null hypothesis, this can be important in some cases. So under the null hypothesis means the expectation of x epsilon is also 0. So its expectation is hidden here. It's 0, and z epsilon is always 0. So the mean minus mean is hidden because they are 0. Otherwise, it's pretty straightforward. And part B, and here the purpose of part A is that at some point we need to estimate some kind of joint distribution. But simplest possible joint distribution we can handle in this question, throughout this question, in the following questions, is this one. If I have chance, I'm going to explain that. So let's have an answer. Simple. So central limit theorem goes like this, and we have 0 and 0. And so by assumption 1, this is always 0, and by the null hypothesis, this is 0. And also, one more thing here is that the variance to equal to this form, expectation something prime, you have to have their expectation equal to 0. Then only when this inside expectation is 0, the expectation of the inside term is 0, then you may write variance as the expectation of quadratic form, squared. So we need the null hypothesis to have this equality. And from here it's straightforward, and you use law of iterated expectations, and then nothing special. Just as usual, we have this. And question B. In question B, we use question A to have we use this result to derive the asymptotic distribution of something like this. Later, you are going to see these guys will change. You may plug in some different numbers in here, and we'll utilize this. And it's also straightforward. You may use a Slutsky theorem. You may use the Slutsky theorem or the continuous mapping theorem to show this, right? Basically, we are just multiplying a vector to a random vector, constant vector to a random vector, and you get this result. And then let's just calculate that, and then this is what you have. This is what you have. And later, as I said, we are going to use some numbers, A1, A2. And now, so nothing special so far. Now it starts, now the GMM part starts. The moment function for the unrestricted model is given by this, because there is only one exogenous variable in the instrument, because it's unrestricted model. So the null hypothesis is not used. We are not sure about the null hypothesis. So we have instrument, and how you implement this. Simply speaking, we have one exogenous variable, so one equation, one moment condition, and one parameter. So one moment condition, one parameter. It's exactly identified, so you don't need any weighting matrix at all. So that's the correct, the best answer is to find out, to point out that we don't need any weighting matrix. The second best answer is to calculate the weighting matrix, but you may calculate the weighting matrix in one step. Let me see if I write something. So this is standard method. I didn't say anything. So you may calculate the weighting matrix, but that is not wrong, but not the best way, not the efficient way to solve this problem, right? And it's super easy. The GMM unrestricted estimator is obtained this way. So far, it is simplest possible instrumental variable regression model, right? Just one endogenous variable and one instrumental variable. So most of you have done really well up to this point. Now the problem starts here. Let me show you my answer. And now I am going to write this notation, AX and AXX. So they are just sample averages of the subscript variable for simplicity of the notation. And then in question E, we are now dealing with this null hypothesis. This is the null hypothesis, or this is the restriction imposed by the null hypothesis equals to 0. Restriction function is what we have here. And you may estimate this guy, this value, using unrestricted, actually I have to put subscript U, unrestricted estimator beta head. And my approach here is, I'll show you my approach first. I'm going to plug in the formula closed form solution for beta head here, and then plug in plug in at y equals to x beta plus epsilon, and plug this in to here and here. Then you will get, so remember, AXY is something like this, x times y as sample average, and then it becomes y is replaced by x beta plus epsilon. So this average becomes AXX, sample average of x squared times beta 0 plus the sample average of x times epsilon I, right? So there's nothing special. It's pretty much the standard way. And also you can do the same thing for the sample average of z times y. And then if you plug these guys in here and here and here, and then you will get this result. Simply, you are going to get this, where A is these two guys and B hat is these guys. So we are going to have this become epsilon, and these guys will be cancelled out. Beta 0 will be cancelled out by this subtraction, and the multiplied numbers will be denoted as b hat. Now remember that what's important here is this guy. This is what we derived in part B. In part B, this is sample average of x epsilon, sample average of z epsilon. We know their asymptotic joint distribution. We know everything about its distribution in the limit. So we know how it behaves. Also, we know b hat here. B hat converges in probability to this guy. So 1 is converging after multiplying square root n. It converges in distribution to a normal distribution. And b hat converges in probability to a constant. So as a result, combining those two results, you have the convergence in distribution, convergence in probability. You may apply the Slutsky theorem, and you get this result. This is the result. And if you want to study the variance, it's a little more complicated. Complicated part comes up here, but it's simple algebra, and you don't need to do it just because it's still correct enough and detailed enough or concrete enough. You don't need to calculate everything in the final step, but if you want, you may do this way. And I may simplify this as using the correlation coefficient between x and z, right? I forgot this typo. It should be squared. I forgot. So squared. So it should be squared. So if you define it this way, you have to put square here and of course square here. Not a big problem, but anyhow, it can be simplified, and you know how to estimate that. Sigma squared, you know how to estimate that, and population mean, easy to estimate, and same correlation coefficient, also you know how to calculate that. So you may estimate the variance this way, and then the wild test statistic is constructed this way. Here, the restriction is just one-dimensional, so you don't need to use matrix inverse or transpose. Simply, what you have is this, and actually, you do not need chi-square. You can do it in the normal distribution with two-tailed test, but for the to be consistent with our unified framework, I'm just showing you how it follows a chi-square distribution. So it follows a chi-square distribution with degree of freedom 1, because the number of restriction was only 1. There was only one restriction about the exogeneity of x. Okay, this is how we utilize the result from part B. Then other than this part, this is annoying, but it's not that difficult. Other than this part, there is no special special theory. Just we learned everything. It's a matter of how you combine things and summarize things here. And one comment here. Some of you have used delta method. The problem with delta method here is the function r is unknown. It's basically population expectation. So you have to replace it with sample average. So r should be estimated again by r hat. So the delta method does not work directly. There are theory to utilize the function r, but that requires the uniform convergence or the stochastic continuity we learned last week. So that is not correct, at least without further detailed proof. So that is not right. And another possible approach is using the randomness in beta hat. We know how to derive the asymptotic distribution of beta hat. That is right. That is right. And actually, that's how I explained in class. In class, I explained as if you can just write it as you can derive the asymptotic distribution from the distribution of beta hat. That is possible. That is possible, but again, it requires more conditions. And then the main problem here is you have to calculate the randomness in beta hat, and also there are another part of the estimate that has another randomness, right? So for example, it has epsilon inside y, so you have to calculate their joint distribution, their covariance. That is the annoying part. In the end, that will be similar to what we did here, right? So that would be similar to, so z epsilon is basically related to beta hat, and x epsilon is related to x times y. So you may use this result to handle the joint distribution between this and this. But that is possible, but this is the simpler way. I am going to rewrite beta hat as a closed form solution so that you can get an easier version of the joint distribution. So I appreciate all of your effort. You have tried a lot, and most of them are not wrong. All your attempts are reasonable. I understand why you try that, but the problem is, the proof is not complete. For the proof to be complete, you need to learn much more detailed, more complicated theories, and that would be nice if you are interested, but maybe you have no time. So let's see if you can follow this. This is the easiest way to handle the question. Okay, thank you. I'm going to continue the next question and the next video. Bye.